Okay, so 15.2 about equilibrium constants, we start to talk about equilibrium in a quantitative fashion. In 1220, very often we want to get down to the details of what kind of mathematical inferences can we make based on the models of our chemical systems. And so let's consider this reaction. 2I gas, those are individual iodine atoms in equilibrium with an iodine molecule. And this is going to be a unimolecular elementary step, this is going to be a single step reaction mechanism. It is bimolecular in the forward direction and unimolecular in the reverse direction, but my main point here is that we can talk about the rates of the forward and reverse reaction using the tools we learned in reaction mechanisms. So the forward rate, we'll call that rate 1. That is going to equal K1 times the concentration of I squared. And rate 2, or I'll call it rate -1. Rate -1, the rate of the reverse reaction, is going to equal K -1 times the concentration of the iodine molecule. And figure 15.3 shows us sort of something familiar, and that is that over the course of the reaction, if we start with iodine atoms, then the concentration of I2 will start at 0. The concentration of I will start at some high value. And then over the course of the reaction, we'll build up some I2, we'll lose some of the I, and that's shown on the left of that chart. After some point, those concentrations will be steady, and that's what we call equilibrium. If we look on the right side here, then we can look at how the reaction rates in the forward and reverse direction will change over the course of the reaction. The forward rate, K1 times the concentration of I squared, will start high, and it will begin to drop as the iodine atoms are consumed. The reverse rate, K-1 times the concentration of iodine molecules, will start at 0 because there is no iodine molecules, and it will rise as we build up I2. And they will reach a point where that forward and reverse rate are equal to each other, and that is equilibrium. Okay, well, we can make use of that definition of equilibrium to set these two rates equal to each other. Rate 1 is equal to rate -1. A familiar exercise from when we were analyzing reaction mechanisms with a pre-equilibrium. So we'll say that rate 1 is going to be equal to K1 times the concentration of I squared, and rate -1 is equal to K-1 times the concentration of I2. Only this time, instead of trying to solve for the concentration of some reaction intermediate, let's just put all of our concentrations on one side and all of our constants on the other. So K1 over K-1, that's going to equal I2 over the concentration of I squared. And this quantity right here, those in particular are the equilibrium concentrations, right? Because rate 1 is only equal to rate -1 once those concentrations have settled into their equilibrium values. And so this quantity is sometimes called KEQ, or just K. This is the equilibrium constant. And equilibrium constants are going to be central to so much of what we're going to do in this course. So a couple of quick notes. We're going to be really sloppy with units for a second here. I promise you there is a justifiable, detailed reason for why equilibrium constants are unitless, but we don't want to get into those details. So even though this looks like a molar concentration, divided by a molar concentration squared, and so you could do the math and figure out that the units maybe should be inverse molar. Well, forget that. Equilibrium constants are always unitless. Just throw away the units like you've always wanted to do since 1210, and your professors never allow you to, and keep insisting to be careful with the units. This is one time, just throw the units away. And then another thing I want to state is that these are not fixed numbers. You can have equilibrium conditions that have different values for I2 and for I that still satisfy this mathematical requirement. Let's take an example. I don't know the actual value for KEQ in this case, but let's just pretend that KEQ is equal to the number 2. So let's look at a couple of different conditions. So I think if I2 were equal to 2 molar and I is equal to 1 molar, then we could plug those numbers in here, and those concentrations put into this formula would equal the value for KEQ. And so this would be a valid set of conditions that describes chemical equilibrium. A mixture with these concentrations would remain at those concentrations. There would be no net change in the concentrations as you move forward. Okay, well, what if we had the concentration of I2 equal to 8 molar, and the concentration of I minus, oh, that's not I minus, of just I equal to 2 molar. Well, let's put these numbers into the expression here. I2 is 8 over 2 squared is 4. 8 divided by 4 is 2. And so these conditions here also satisfy this formula for the equilibrium constant. And so a mixture which contains 8 molar of I2 and 2 molar of I is also at equilibrium. Which of these your reaction will end up at depends on your starting conditions. And there are, of course, infinite other combinations which satisfy this equation here. And so it depends on what your starting conditions are. How much iodine and how much iodine molecule and how much iodine atom did you start out with at the beginning of your reaction? And sort of mathematically dealing with that will be the subject of section 15.5, I believe. But for now, let's just recognize that there are a whole family of conditions which will satisfy this mathematical expression. And this, by the way, is called the equilibrium expression. The whole equation here, that KEQ is equal to the concentration of I2 over the concentration of I squared. This formula here is called the equilibrium expression. K is called the equilibrium constant. Okay, so we've been talking about this particular example, but let's go ahead and generalize it. In order to make this argument, I had to state that this is a single-step reaction mechanism, and we had to look at the individual forward and reverse rates, and that makes this maybe a not very generalizable approach to all sorts of chemical equations that take more than one step, etc. Now, I won't show the proof of it, but we can actually extend that same idea to any reaction, whether it's single step or multi-step or anything else. And so, in general, let's write a form of a reaction AA, BB in equilibrium with CC plus DD. So here the uppercase letters are just different chemical compounds or elements, and the lowercase letters are the stoichiometric coefficients in a properly balanced chemical equation. So this could represent any chemical reaction. Well, we can say that KEQ, that equilibrium constant, is going to equal the concentrations of the products, each raised to the power of their stoichiometric coefficient. So that stoichiometric coefficient becomes an exponent here, and that stoichiometric coefficient becomes an exponent there. And then we'll divide that by the concentrations of the reactants, and those reactant concentrations are similarly raised to the power of their stoichiometric coefficients. So now we have a general form of equilibrium expressions. The equilibrium constant is equal to the concentrations of the products raised to the power of their stoichiometric coefficients divided by the concentrations of the reactants raised to the power of their stoichiometric coefficients. And I haven't shown a proof of why that is the case, even when you have complex reaction mechanisms, but you can just trust me on that. Products over reactants raised to the power of their stoichiometric coefficients. Now there's one more important little thing here. A gas or an aqueous solution will have a concentration here. Molar concentration, moles per liter. For aqueous solutions, we're very used to dealing with what the molar concentration is of an aqueous solution. For a gas, all we need to do is take PV equals nRT and rearrange that. N over V, the molar concentration, is going to equal P over RT. And so it's pretty straightforward about how you could convert a gas at a given pressure and temperature into a molar concentration. So gases and aqueous solutions will show up in the equilibrium expression, but pure substances, solids and liquids, are absent from the equilibrium expression. You will not include the concentration of water. That is a pure liquid. You will not include the concentration of solids, say a solid salt if it isn't dissolved, or something like carbon or anything else like that. Solids and liquids do not show up in the equilibrium expression at all. You just ignore them. Okay, so we had talked about a reaction between nitrogen and hydrogen and ammonia in section 15.1. I'll go ahead and write it in the reverse direction now, just to show that we can do that and there's nothing wrong with that. So we'll have 3H2 gas plus N2 gas in equilibrium with 2 NH3 gas. This particular reaction is the most important reaction in the chemical industry. It was critical to the Industrial Revolution and the Agricultural Revolution that the easy production of ammonia is an essential part to so much about what makes our modern life possible. As far as like metric tons per year, this reaction dwarfs all other reactions that are carried out in the chemical industry. So it's a very important reaction. Can we figure out, and it is an equilibrium reaction, so can we figure out the equilibrium expression for this reaction? Well, we'll take the concentration of the products, NH3, and we'll raise them to their the power of their stoichiometric coefficients. There's squared because of the 2. And then we'll take the concentrations of the reactants and we'll raise them to the powers of their stoichiometric coefficients. We're going to cube the hydrogen, and then the nitrogen will just leave as a 1. They're all gases. There's no solid or liquid, so everything should be present. And there it is. That is the equilibrium expression for this reaction. We can get different equilibrium conditions depending on the initial conditions, how much hydrogen, how much nitrogen, how much ammonia did we start with. But the value K itself will be the same regardless of your starting conditions. All of your concentrations will change over the course of the reaction until they reach the point where they satisfy this expression. Everything conforms to K. K is the governor in this process. However, I'll just throw out there for now that that K is a function of T, function of the temperature. So once you start changing the temperature, then the equilibrium constant will actually change as well. And we won't get into that right now about how and why it changes. But just be aware of that. Your equilibrium constant is valid for the single temperature that it was given to you. Now, let's look at this right now and kind of look at the form of this. It's always going to be products over reactants. And so the value of K can tell us something about the reaction at a glance without having to do any math or anything. The values for K span a huge range. You could have a K that is much greater than 0. Say you have a K that's on the order of 10 to the positive 12th, or that would be what, a trillion. Thousand, million, billion, trillion, yes. So if you have a K that is much larger than 0, then that means that your numerator is very large and your denominator is very small. So we will call reactions that have K much larger than 0 product favored. Okay, and I don't need to do any math. I can't tell you exactly what the equilibrium concentrations are, but just at a glance, if K is much larger than 0, then I can tell you that, well, it's pretty much mostly going to be product, and there will just be some trace amounts of reactant left over. K is also often, for some reactions, much less than 0. You've encountered weak acids and weak bases before. Well, weak acids and weak bases have reactions with Ks that are much less than 0. And what that means is that you have a very tiny numerator and a very large denominator. And so you have not very many products and lots of reactants. This is a reactant favored reaction. And of course, you will have some reactions where K is, oh goodness, I'm so sorry. K is always a positive value because your concentrations are always positive values. I guess me making mistakes like this on camera can help model for you how to recognize when you've made a problem and correct it. So what I meant was Ks that are much larger than 1. So that doesn't change your argument very much. Something like K is equal to a trillion is still product favored. Ks that are much less than 1, they will still be positive valued, but they will be very small. Something like 10 to the negative 12th, or 1 trillionth. And so 10 to the negative 12th is still a positive number. It's just very, 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 very small. And that would be, if k is equal to 10 to the negative 12th, that would be an example of a reaction which is reactant favored. Okay, and now back to where I recognize my mistake. There are some equilibrium constants that are close to 1 itself. And those are, in some ways, the most interesting reactions. Those are the ones where you actually have a good, healthy balance of both reactants and products at your equilibrium condition. You can't easily say that it's product favored or reactant favored. It's really going to have a good, healthy mixture of both of them. Okay. One last thing to say about equilibrium constants. Technically, I have been talking about only one type of equilibrium constant. So far, I've been talking about Kc, a concentration equilibrium constant, which is going to equal, oops, we'll go back to our generic reaction formula, C raised to the C, D raised to the D over A raised to the A, B raised to the B. Now, if all of your reactants and your products are gases, you don't want to have to go to the hassle of converting all of your gas pressures into concentrations. Measuring gas pressures is a natural and normal way to measure the amount of gas that you have. Concentrations, not so much. And so in order to save yourself the step of converting all of those pressures into concentrations, we can also talk about equilibrium in terms of pressures. Kp is the equilibrium constant expressed in terms of pressures instead of concentrations. And it's going to have the same form, except it'll have pressures instead of concentration. So the pressure of C raised to the power of C. The pressure of D raised to the power of D. The pressure of A raised to the power of A. And the pressure of B raised to the power of B. So these represent the same conditions, but because one is measured in molar concentration and one is measured in pressure, they're not necessarily equal to each other in value. If we think about how pressure is equal to nRT over V, and N over V is just the molar concentration, then the pressure of X is equal to the molar concentration of X times RT. Is that fair? If I look at Kp now and I kind of put this expression in for all of my pressures, then I would get the concentration of C raised to the power of C times RT raised to the power of C. And I would get the concentration of D raised to the power of D times RT raised to the power of D. And down here I would get the concentration of A raised to the power of A times RT raised to the power of A, because that is what the pressure of A equals. And then the concentration of B raised to the power of B times RT raised to the power of B. Okay, so this looks like a mess, but we can clean it up quite a lot. C raised to the C, D raised to the D, A raised to the A, B raised to the B. What is that equal to? Well, that's just Kc. Kp is equal to Kc times, now we've got all of these RTs, and that's going to be C plus D minus A minus B, because we have a C and a D in the numerator, a and a b in the denominator. And c plus d minus a minus b, this is all what we're going to call delta N, the change in the number of moles of gas in a given reaction. So Kp is equal to Kc times RT raised to the power of delta N. Let's look at that in the context of a familiar reaction. So let's go back again to 3H2 plus N2. Phase is important here. Those are both gases in equilibrium with 2NH3, also a gas. Let's count how many moles of gas we have on the reactant side. 3 moles of gas on the left. Oh, I'm sorry, that's not true. We have 4 moles of gas on the left side. 3 hydrogens and 1 nitrogen. And how many moles of gas on the right side? 2 moles of gas on the right side, 2 ammonias. And so what is delta N for this reaction? It will be -2. Our change in the moles of gas is -2. We went from 4 to 2, which means that for this reaction, Kp is equal to Kc over RT squared. Because RT raised to the power of -2 is equal to 1 over RT squared, right? So Kp is equal to Kc over RT squared, which makes this relationship temperature dependent. Definitely Kp and Kc are not equal to each other in this case. Now if you had a delta N equal to 0, that is the one time when Kp and Kc are precisely equal to each other. But for all of the other gas phase reactions, you'll need to have this relationship. Kp is equal to Kc times RT raised to the power of delta N. Okay, and that's it for 15.2.